Unit 2, Forces and Newton's Laws. Lesson number 4, Forces, Free Body Diagrams, and Newton's First Law. Let's start by defining force. Force is defined as a push or a pull on an object. The symbol for a force is the capital letter F. It's a vector quantity, so we'll put an arrowhead on the top. Whenever there is an arrowhead, we know that we're talking about a vector, so there should be a direction associated with the force. The unit of measure is the Newton, named after Sir Isaac Newton, and is given the symbol capital N. A Newton is the amount of force that's required to give a 1 kilogram object an acceleration of 1 meter per second squared. So 1 Newton is equal to 1 kilogram times meters per second squared. This is just some information that will help you understand where this unit came from. You can put it aside and remember where you wrote it down. Let's talk about some everyday forces that we encounter. The first one is the force of gravity, and we give it the symbol F with a subscript little g. This is defined as the force of attraction between all objects. The force of gravity between the Earth and objects is directed towards the center of the Earth, and it is what we call an action at a distance force. So even though you might be a little bit far away from the surface of the Earth, you'll still feel the effects of gravity. If you are significantly far away from the Earth, then you will no longer feel it. But we call it action at a distance force because the force can still be felt even at a small distance away from the object. The second force, which you may not be familiar with or may not have heard before, is called the normal force. And I want you to imagine standing on the floor. So we have a person standing on the floor, and we know that the force of gravity pushes down on this object. So the force of gravity will push down. What keeps us from falling through the floor is the fact that the floor itself exerts a force up onto us. And this force that the floor or the surface exerts up onto us is called the normal force. And if it weren't there, we'd fall through the floor. Imagine the floor was replaced with a thin sheet of tissue paper. You would know that you would fall straight through that sheet of tissue paper. But the reason we don't is because whenever we press down on the floor presses up onto us. So the normal force is defined as a force that is perpendicular to the surface of the objects in contact. Another common force is the force of friction, and we'll study this force in further detail. It's a force between any two objects that are in contact. We have two types of friction, static friction and kinetic friction. Static friction is a force that prevents stationary objects from moving. And kinetic friction is the force of friction that acts against an object whenever it's in motion. Air resistance is also a form of friction, and it's friction that acts on an object moving through the air. The third example, I want you to imagine a box being pulled by a rope. This force that the rope is exerting on the object is called tension. If you notice, you're not touching the box itself, the rope is touching the box. And the tension is the force that exists within this rope. So tension is defined as the force exerted by strings, ropes, cables, and fibers. As we mentioned, the SI unit, the System International Unit for force, is the Newton, whose symbol is capital letter N. When studying forces, it's important that we know how to draw them. When we draw forces, we need a scale. For example, 1 centimeter represents 20 newtons. One that allows us to effectively draw the force on a sheet of paper so that we're not drawing a very big diagram when we're dealing with very big forces. The second is to include reference coordinates so we know where north, east, south, and west are, or up, down, left, and right. You must include these when you're drawing a free body diagram. We're going to look at a few examples, and we're going to examine the forces that are present acting on these objects. The first one is your notebook resting on your desk. If you're drawing a free body diagram, that's what we call these force diagrams, free body diagrams. You'll draw the object free from its environment. So here we're talking about the forces that act on a book. So when we do this, we're going to draw the book itself. We don't have to draw the desk. All we're looking at are the forces that are acting on the book itself. Okay? So let's examine what forces exist on this book. Well, the force of gravity will pull down on the book. And since the book is not falling through the desk, we know that there must be a force that is supporting it upward. And that force must be equal in magnitude, in size, and opposite in direction from the force of gravity. And we call that force the normal force. If you were to draw a scale body diagram, the size of this force of gravity must equal the size of the normal force. This tells us that the object is not moving up or not moving down because of these forces, that it is at rest on the surface of the desk. Okay? The second force that we're going to draw is the forces that are present on a tennis ball that is falling through the air. So let's draw this tennis ball. And if it's falling through the air, we know that it's going to be traveling in the downward direction. What is causing it to fall? Well, the force of gravity is causing it to fall. Since it's not resting on a surface, there's no upward force or no normal force. The only force that's acting on this object is the force of gravity. Next, we'll look at a child on a toboggan. A toboggan is another term for a sled. So let's draw a child on a toboggan. It's a Canadian winter, so this child is all bundled up and tobogganing in the snow. So, there's a force of gravity pulling this object down. Since this individual on the toboggan is on the planet Earth, we cannot get away from the force of gravity. Since he's not falling through the ground, we must know that there's a normal force acting up on the tobogganer. And the only other force that exists, which is going to slow this guy down slightly, is the force of friction. So if this child on his toboggan is traveling in this direction, moving right, friction always opposes motion, always goes in the opposite direction. And that's why eventually in the real world, when things are moving forward, objects tend to slow down. And what causes them to slow down is this force of friction. Okay. You can't study forces without introducing the concept of inertia. Every object possesses a property that Newton called inertia. Let's imagine that we release the ball, so it travels down a ramp, across the ramp, and is allowed to go back up the other side. If there's no friction, the ball will move down the ramp and up to the same height it was released, then back down and up forever and ever and ever. If there were friction, then eventually the ball would slow down and rest somewhere in the middle. But Newton and other physicists like Galileo had a thought experiment. What if we decreased the slope of this line or the ramp so that eventually it ended up flat? What would an object do if it were released from this height and there were no friction? Well, Galileo thought this object would probably continue moving in a straight line forever and ever and ever. And he was correct. And he said that the reason why objects do this is because they have a property that all objects possess called inertia. And inertia is defined as the property of matter that causes a body at rest to resist changes in its state of motion, or a body in motion to resist any changes in its state of motion. So a simple way to describe the principle of inertia is an object at rest continues to remain at rest, and an object in motion continues to remain in motion This principle was discovered early on. It wasn't until a little bit later when Newton did some more work when he explained it with a lot more understanding. So your job is to understand the principle of inertia. As we move on, we're going to talk about a net force. Oftentimes there are several forces acting on an object, and these forces together cause an object to move in a particular way, in a particular direction. The direction in which they move depends on the net force. This is the sum of all of the forces acting on the object. So if we can add up all the forces acting on an object, we will find the object's net force. Another way to describe the net force is by calling it the resultant force, or the total force. The total of all forces. And we give it the symbol F subscript net. So let's look at an example. Example, a weightlifter holds a weight above his head by exerting a force of 1.6 kilonewtons. And know that 1.6 kilonewtons is 1.6 times 10 to the power of 3 newtons. To go from kilonewtons to newtons, you multiply by 1,000. And to go in the opposite direction, to go from newtons to kilonewtons, you divide by 1,000. In part A, they want us to draw a free body diagram of the weight, and they want us to state the net force. So we'll draw a weight. And we know that there is the force exerted by the weightlifter in the upward direction. We'll call this the applied force. We'll give it the little subscript A for applied force, and it's 1.6 kilonewtons. We also know that the force of gravity is 1.6 kilonewtons down. So these two forces should be the same length because they're equal in size or magnitude. If we want to find the net force acting on these objects, the net force is equal to the sum or the total. It's going to be equal to the force applied by the weightlifter plus the force of gravity acting down on the weight. So we can put in these values. That's 1.6 kilonewtons up plus the force of gravity is 1.6 kilonewtons down. Since these are vectors, we cannot add vectors unless they are in the same direction. We learned in Unit 1 that you can change the direction of a vector by changing its sign. So we can change these both to up or both to down. Whichever you decide to do will not make a difference. You'll get the same answer. Trust me on this. I'm going to change them both to up. So the first one will remain the same. It's 1.6 kilonewtons up plus I'm going to change this 1.6. I'm going to change its sign to negative 1.6 kilonewtons. If I change the sign, I will change the direction. So it'll go from down to up. So we have 1.6 kilonewtons up plus negative 1.6 kilonewtons up. Now we can add these into our calculator. 1.6 plus negative 1.6 equals 0. So the net force is 0. That means that this weight is not moving up, it's not moving down, it's staying where it is because all the forces balance. We have 1.6 kilonewtons up and 1.6 kilonewtons down, which gives us a total force of 0 newtons. Let's look at Newton's first law. It's your responsibility to know all three of Newton's laws. The first one is written like this. If the net force acting on an object is 0, the object has two possibilities for its motion. The object is either at rest or moving at a constant velocity. So whenever the net force is 0, that means that the object is either not moving or moving at a constant velocity. Okay. In the example above, they asked us in part B to determine the net force if the weightlifter applied a force of 1.8 kilonewtons up. So let's find the net force. It's the applied force by the weightlifter plus the force of gravity. The force of gravity is still 1.6 kilonewtons down. But now the weightlifter is applying a force of 1.8 kilonewtons up. Let's add these two together. First, ask yourself, are they in the same direction? In this case, they're not. So what we need to do is change this to negative. I'm going to skip a little step here and I'll show you what I've done. Change this to negative up. So we have 1.8 kilonewtons up minus 1.6 kilonewtons up. So I've just changed the sign and changed the direction, and now we can proceed algebraically. The net force acting on the weight, since the weightlifter applied a slightly larger force, is 1.8 minus 1.6, which is 0.20 newtons. Now here's a little hint. If this force gets bigger, then this is not working the way I want it. If we make this force bigger, then the weight is going to start to move up. And one of Newton's laws describes what happens when we change these forces when the net force is not zero. That'll be coming up in the next lesson. Okay, let's summarize Newton's first law of motion. If the net force acting on an object is zero, the object will remain in its state of rest or in a state of constant velocity. We can summarize the first law by stating four important results. Letter A, objects at rest remain at rest unless acted upon by a net force. B, objects in motion remain in motion unless acted upon by a net force. If the velocity of the object is constant or zero, then the net force must be zero. If a velocity of an object is changing either in size or in direction or both, then the change must be caused by an external force, which we will discuss in Newton's second law. Your job is to try these homework practice questions and the LMS quiz that goes along with this lesson. Good luck.